Hello, welcome to the second Jedi lesson. This is week 2, homework 2A on Wiley Plus, and we're looking at question 2. So, a positive charge is moving from point A to point B in a uniform electric field, as shown in the drawing. The electric force does blink work on the charge, and as a consequence, its electric potential energy blink. So we have this model here that's helpful to us in the problem. Oop, I don't want to show the correct answer. So we're going to work from there, and a few things to note while we're working through the problem. We have WAB, which will be representing the work done by the electric field when moving from point A to point B. And the SI units are in joules. And then the next thing that I want to go ahead and define is delta EPE, which is the change in electric potential energy. And that's also represented by subtracting the electric potential energy of B minus the electric potential energy of point A. And the SI units are also in joules, which is represented by our J. So with that in mind, we also want to take note of the equation that is helpful to us, which is delta electric potential energy equals EPE from point B minus EPE from point A, and that equals the negative EP. And we're going to go ahead and work through this problem. So the first thing we want to keep in mind is that the electric field lines point right, and this is because since the positive charges feel force along field lines, their force is going to point right. So since the charge is moving left from A to B, the force and displacement in our problem oppose each other. So since we have opposing directions, like in this diagram here that we have, then that indicates that our work is negative. And then as for the electric potential energy, which is answering the second part of the problem, we want to keep in mind that the system energy depends on the work done, which is represented here. And since we're using the equation that I wrote down here, it could also be written as this. Make it a little bit shorter. And negative work yields a positive energy change. And so positive change means that the energy is going to increase in our model. So this is also similar to, I guess, like mass against gravity, like going against each other. So the stored energy goes up during the move. And so with this in mind, then we know that the electric potential energy is going to increase. So again, we have that electric force does negative work on the charge, and as a consequence, its electric potential energy increases. So we're going to go ahead and check that. And we got it correct here. All right, and with that, we're going to move on to the next problem. All right, so looking at the third problem that we have, it states that the drawing shows 3 arrangements of charged particles, all the same distance from the origin. Rank the arrangements, largest to smallest, according to the total electric potential V at the origin. So we have 3 different models that we're looking at, and I just want to start off by giving us some useful definitions. So we know that V, which is stated here, stands for the electric potential. So electric potential is a scalar quantity and not a vector. So with that said, that means that we don't have to worry about any angles in this problem or anything like that, and we could just add the values together. So the formula that we'll be using for this problem here is V equals KQ over R. And I'm going to go ahead and define each of those variables and give the SI units for those as well. But first, because every single charge in all 3 drawings is around the same area or the same distance from the origin, which is represented by R, then the total potential is directly proportional to the sum of the charges, which is sigma q. So with that said, I'm going to define some of these variables that we have. So K in this equation is Coulomb's constant, and Coulomb's constant is roughly 8.99 times 10 to the 9th. And then the SI unit for this is n times m squared, c squared here. And then for Q, it represents the fundamental charge unit. And we know that this has SI units of a coulomb, which is represented by C. And the last variable I want to define is R, which is the distance from point charge to the origin. And the SI units for this are meters. All right, so now that we have this, so we're going to go ahead and solve the problem. So first we have A, And we're going to start off with what we know. So we have the negative 2q and then the positive 6q. So again, like I stated earlier, since this problem has scalar quantities, not vectors, then we're able to add up the values together. So we're just going to add up the negative 2q plus the positive 6q, and that gives us a total of positive 4q. We're going to repeat those steps for arrangement B and arrangement C. So for B, we have the positive 4q plus negative 2q is positive 2q. And for C, we have positive 5q plus positive 7q plus the negative 3q, and then plus the negative 5q equals positive 4q. So off the bat, we can see that A and C both have the same electric potential, but they're also the largest electric potential. So then we know that A and C have the largest. And then B has a positive 2q, which means it has the smallest electric potential. So then our answer for this problem should be from largest to smallest, since these are equal. I just put ACB. Should be ACB. And A and C should be tied, so let's go ahead and check that. And checks out.